There is just one general subject which I wanted to discuss today about just the capacitor. We saw that when capacitor is charged, it stores energy in the form of potential energy, and we can associate this energy with the existence of the field. We will use this fact sometimes at the end of the semester when we will be talking about electromagnetic waves, because electromagnetic waves allow transport of energy through space in a form of electric and magnetic field, and part of that, exactly half of it, is carried in a form of electric field. So I wanted to introduce concept of energy density and associate energy density with the properties of the field. By definition, whenever we speak about density, it's always the same. It is something per unit volume. So like we had charge density, it was charge per unit volume. If it was mass density, which we refer to as just density, it was amount of mass divided by the volume in which this mass was contained. So energy density will be also defined in a similar way. If we have electric field, imagine, for example, that we have electric field over here. So energy density at this location of the space would be the amount of energy contained in a tiny fragment of that space associated with, well, in general, whatever, divided by that volume. Now, I wanted to talk about electrical energy density, so it will be du, therefore, how about if we take a look at the field? Let's say that we have some kind of field. So if I want now to determine what is energy density in a particular location, let's say over here, I have to imagine a block, a cube, and find out how much energy is in this volume due to the presence of electric field, and divide by that volume. This will give me electrical energy density. All right. So electrical energy density, I mean, if let's say that now how to harvest it. So I will see how much energy I can get from this field until I damage it, until I destroy it. So I'll take two parallel plates which are conductive. Well, if this is electric field, then it means that it appears like a charged capacitor. Can you see that? On which side will the potential is going to be higher, on the top or on the bottom? In other words, which plate will be plus and which plate will be minus? So who votes that the top plate will be plus? You are right. Those of you who believe that this plate has higher potential, this lower, you are right, because electric field between the plates is downward. All right, let's say now that the separation between the plates is dx. And let's see how much energy we can get from that. And divided by the volume. Right, so it looks like a charged capacitor. So energy stored in this capacitor is, I will take one of those three formulas. It is 1/2 charge of the, capacitance of the capacitor multiplied by square of the potential difference between the two plates. This gives me energy stored in that capacitor. And here I have to divide it by the volume of the capacitor. And I have the area of the base. I have the separation between the plates. So area of the plates times separation gives me the volume. All right. So now let's explicitly relate it, substitute the potential difference and capacitance with the formulas which we derived before. So instead of capacitance, I explicitly related to the shape of this capacitor and the property of the space, and I'm having it in a in space. So well, actually, no matter what, I can have any type of a medium. So capacitance will be dielectric constant of the medium times permittivity of free space. Here I have area of the plates and the separation between the plates. This fraction or this expression represents capacitance of this small capacitor. Now, potential difference between the plates is related to the electric field vector. And, well, recognizing that the electric field vector is vertical, now separation is also in this vertical direction, so potential difference is equal to just magnitude of the electric field times separation of the plates. Well, then the rest is just algebra. I have dx over here squared. It cancels with this dx and it cancels with this dx. The area here cancels with this area. So the expression which is left is just 1/2 the electric constant of the medium, permittivity of free space, and square of the electric field strength. So the electric energy stored in space is proportional to square of the electric field strength. So if electric field strength, for example, I mean, when electromagnetic wave, for example, travels through this point, electric field grows, decreases, grows, decreases, grows, decreases. It oscillates. And it oscillates in a random way, but for example, if you consider a particular broadcasting station, like Fox 4, for example, in Kansas City, then that electric field over here will even oscillate harmonically. This will be a sinusoidal function of time. So if electric field has the maximum value up, the energy density at this point will be the highest or lowest or in between. Who votes that it will be highest? It is going to be highest. Now there is an instant that electric field here is 0. How much energy density is going to be here then at that instant? 0. Now when the electric field has lowest value, what will happen with energy density? It will have the highest value, intermediate, or the lowest. Who votes for highest? And you are right. Those of you who, because we have to square it. All right. So that's it for a single capacitor. Now I wanted to get closer to circuits and talk about systems of electrical elements. What will happen if we connect elements? And today I'm going to talk about what happens, how a system of capacitors behaves. And, well, we will find out that a system of capacitors behaves like a single capacitor. And then we will determine what is capacitance of a system of capacitors. Now, we can say about capacitance only because first we have to recognize that a system of capacitors behaves like a single capacitor. If a system of capacitors did not behave like a single capacitor, then it wouldn't be true. Concept of capacitance wouldn't make sense. All right. Well, we have three possibilities for connections. One is referred to as connection in series. And connection in series means that if I have two elements, or if I have a lot, certain amount of elements, if certain amount of charge enters one element, the same amount of charge has to enter the second element. These are not the same particles carrying the charge, however. So let's say that we think about one electron enters this device, or this element over here. It would mean, if elements are connected in series, in the same amount of time, one electron has to enter the second element. What happens with the charge determines if connection is in series, in parallel, or other, not how geometrically it is arranged. And I'll show you examples. These are academic examples in which will be hard to say if they are connected in series or in parallel, but they will be in a particular way. Now, a parallel connection means that the devices are connected in such a way that potentials on corresponding sides are equal. So, if elements are connected in parallel, let's say that I take this element, potential on the left-hand side of this element is equal to the potential on the right-hand side of this element, and on the left-hand side of the second element, and potential on the right-hand side of the first element is equal to the potential on the right-hand side of the second element, which means that these two elements are connected in parallel. If we can recognize that no matter what happens, no matter how, let's say, if these are capacitors, no matter how we charge capacitors, potentials on corresponding sides will be equal, then the elements are connected in parallel. We could have, however, that if we can recognize that potential on the left-hand side of the top element is equal to the potential on the right-hand side of the bottom element, and potential on the right-hand side of the top element is always equal to the potential on the left-hand side of the bottom element, these two elements would be also connected in parallel. And finally, there are other connections, like, for example, this connection. These elements are neither connected in series nor in parallel. All right, let's now see that indeed, if I connect capacitors in parallel, then that system is going to behave like a capacitor, and we will determine what is capacitance of this capacitor. Well, so let's say that I arrange capacitors in such an arrangement, and how to check if this, well, first of all, do we recognize that it is a connection in parallel? Well, in order to recognize if it is in parallel, what would we have to know? No, we don't need the charge. We have to recognize that, let's say, if potential here is a 0 and here is 1, on the remaining capacitors I would have to have also potentials 0 and 1. The potentials have to be equal on corresponding sides. So let's say that I have potential 0 here and 1 there. What potential I'm going to have here? 1. Is it equal to the potential there? Yes, so right-hand side of the top capacitor has the same potential as the right-hand side of the bottom capacitor. Now, potential here was 0. What is potential here? Also 0. So no matter what, now let's say that I have 5 and 6. 5 volts here, 6 volts there. What will be potential here? 5. And potential here? 6. You can recognize that this is going to be the case. And well, and the reason is because the left-hand sides are connected with a wire. And we will talk about wire more precisely later on. But an ideal wire constitutes an equipotential surface. So everywhere along the wire, potential is supposed to be the same. Therefore, we can recognize that all the left-hand sides of that system have the same potential, and all the right-hand side plates also have the same potential, other than the left-hand side. All right, so let's now say that potential on the left-hand side is V plus, potential on the right-hand side is V minus, and how would I verify that that system behaves like a capacitor? What do I have to check? That potential difference is equal to, or just say proportional, that the potential difference is proportional, well, whatever happens in a capacitor. In a capacitor, potential difference is always proportional to charge transferred from one side to the other side. So this is what we have to verify, that indeed this potential difference for the entire system is proportional to the charge transferred from one side of the system to the other side of the system. This is what we have to verify, that the charge is proportional, charge transferred from one side of the system is proportional to the potential difference. All right, now let's say that capacitors have capacitances C1, C2, and so on. And, well, I have potential difference, potential here, V plus, V minus. So what will be the charge? Can I find the charge on this capacitor? In other words, charge transferred from one side to the other side. Can I find it? Yes. And how? From the definition of a capacitor. Charge is equal to charge transfer from one side to the other side is equal to capacitance. So I mark those charges, and so I can find all those charges. Now, how much charge was transferred from one side to the other side? Well, Q1 plus Q2 and so on. So charge transferred from one side to the other side is equal to sum of the charges on all capacitors. Or in other words, charge transferred on individual capacitors. Now, I can relate this charge to potential difference across the capacitor. It's capacitance of the first capacitor multiplied by potential difference, V plus minus V minus. Charge on the second capacitor is equal to capacitance of the second capacitor multiplied by potential difference across the second capacitor. But since they are connected in parallel, I mean, I recognize that it's the same as before, as for the first capacitor. So I have the same potential difference, and so on. Now I can factor out potential difference, and it should make me happy. And you should be happy now too. Why? Vincent, can you see why? Because? What is equal Q? No, say it in English. Don't say a letter now. I don't want, yes, Owen says, because the charge is proportional to what? Not sum of the capacitors. First of all, this is not sum of capacitors. A capacitance is, okay. But this is not what makes a capacitor capacitor. The charge transferred is proportional to the potential difference, right? And charge transferred from one side of the system to the other side of the system is proportional to the potential difference across the system. So we recognize that indeed this system behaves like a capacitor. And Andrew actually already recognized that this sum has a significant meaning, right? What is that meaning? Because the proportionality coefficient between charge and potential difference in a capacitor is the capacitance of the capacitor. Right, what capacitor I'm talking about now? The system. Very good, right? So we found out that this coefficient is the capacitance of the entire system. So in summary, if I connect all capacitors in parallel, they will behave like a single capacitor, and the capacitance of that system is going to be equal to the sum of capacitances of individual capacitors. All right, let's now take a look at another connection. If we connect capacitors in series, so what will happen if we create potential difference? So let's say that on the left-hand side we have potential V plus, on the left-hand side we have potential V minus. Can I now recognize that, well, let's see if they are maybe they are connected in parallel. I can recognize that potential on the right-hand side of the first capacitor is equal to the potential on the left-hand side of the second capacitor. Maybe they are simultaneously connected in parallel, right? Are they? No. Why not? Because we do not have a guarantee that potential on the left-hand side of the first capacitor is equal to the potential on the right-hand side of the second capacitor. If this was the case, then the capacitors would be connected in parallel, if I knew that always it is going to be the case. All right, now how to see if this system behaves like a single capacitor? What do I have to verify? That's what? No, capacitance is not important at this point. That the charge is proportional to the potential difference. Which potential difference? Across the system. In other words, the potential difference between this point and this point. So V plus minus V minus. Now, if elements are connected in parallel, in series, well, I can recognize that potential difference between this point and this point is equal to potential difference between this point and this point, plus potential difference between this point and this point, and so on. So potential difference across this entire system, I mean, really you can think about it this way, that think about two, just two. So we don't have three, but two capacitors in this series. Then V plus minus V minus is equal to V plus minus this potential plus this potential minus that potential. So I can add and subtract potential in between. Do you understand that? If it isn't clear, let's go to the whiteboard and see on the whiteboard. So let's say this is V plus, V minus, and I will put here VA. So potential difference across the entire system is V plus minus V minus. I can write it down that this is V plus minus VA plus VA minus V minus, right? Because these two add up to 0. Now I will associate these two terms and these two terms. And what's that? This is potential difference across the first capacitor. Now what's this? Potential difference across the second capacitor. So indeed we can recognize that if we add potential differences at a particular instant across all elements, we can get potential difference across this entire element system. Well, capacitors are connected in series, which would mean, and how can I see that they are connected in series? Are they really connected in series? How do I see that they are connected in series? Well, we have to figure out what will happen if charge Q enters this side of the system. So if I have charge Q on this plate, what charge I will have on the other? Minus Q, right. Now how can I get that minus Q over here? Look, that part over here is really isolated. Charge cannot flow out from that fragment. So if charge minus Q is here, what happened with that excess charge from that plate? It moved to the plate of the next capacitor. So charge on this plate is going to be Q. Do you see that? If charge Q enters this plate, by induction it is going to charge this plate with charge minus Q, and it can happen because that charge will flow to this capacitor, charging this plate with charge Q. How this plate is going to be charged? Minus Q. And this one? Plus Q. And this one? Minus Q. All right, so now if I look at this system as a box, what charge is on the left-hand side? Q. What charge is of the system? What charge is on the right-hand side of the system? Minus Q. How much charge was transferred from one side to the other side? Q. Correct. Now let me give you a puzzle. Based on this, what I just said. Let's say that this capacitor, the charge on this capacitor is 1 microcoulomb. Charge on this one, no, microcoulomb. Charge on this one is also 1 microcoulomb. And I have 5 capacitors. Yes, so on each of those capacitors, charge will be 1 microcoulomb, correct. What will be the charge on the entire system? Huh? All right, okay, I hear 5 or 1 or 0. Good. So, who votes for 1? Yeah, recall that charge on each capacitor is 1 coulomb, and we have 5 capacitors. All right, let's vote again. How many vote for that? About 5. Who votes that the charge is going to be 5 microcoulombs? A comparable support. Who votes that it will be 0? Less support, but there is some support. The answer was 1. Yeah, recall what we just said. If we put charge Q on the left-hand side of the first capacitor, charge over here will be minus Q. Charge here will be Q, here will be minus Q. Q, minus Q. If we look at entire system, charge Q was transferred from one side of the system to the other side of the system. Exactly the same amount of charge like for the first capacitor. Charge Q was transferred from one side to the other side. If capacitors are connected in series, remember that each capacitor and the entire system will be charged identically. Adam has a question or a comment. This is only for a series, correct, because we saw that if the elements were connected in parallel, then it's added. Charge is added. Here voltages add up, not charges. All right, now I can find out what relate potential difference across each capacitor with the charge stored on the capacitor and charge stored on the entire system. So potential difference across the first capacitor will be charge across the first capacitor divided by capacitance of the first capacitor. Potential difference across the second capacitor is going to be charge on the second capacitor, which happens to be the same as on the first and on the entire system, divided by capacitance of the second capacitor, and so on. I can factor out this common charge, and I can recognize what? Now look at this. Potential difference. V is potential difference across the entire system is proportional to the charge transferred from one side of the system to the other side of the system. So the system behaves like a capacitor, correct. The system behaves like a capacitor, and on top of it I can recognize what is the capacitance of this system. Well, this is a proportionality coefficient. I have to multiply charge by this proportionality coefficient to get potential difference. Now, in the definition of capacitance, it is the charge is equal capacitance multiplied by potential difference. So if I solve for potential difference, this coefficient is the inverse of the capacitance of the system. So if elements are connected in series, then inverse of the capacitance of the system, we refer to this also as equivalent capacitance of the system. So the inverse of equivalent capacitance of the system is equal to the sum of inverses of individual capacitances. All right. How about if why don't we now take a look at certain connection. So let's turn off the camera. So as the first puzzle, I'm going to draw a diagram of connection, and you will tell me how the elements are connected, how the capacitors are connected. Yeah, I connected capacitors that way. Who believes that they are connected in series? Who believes that they are connected in parallel? Now remember that there is also other connection. Who believes that they are connected in parallel? Who believes that they are connected other way? William, why did you believe that they are connected in series? In parallel. You said in series, right?
I thought series.
Right. Why did you believe that they are connected in series?
Regardless of the other wires, it's still transferred.
Yeah, because they are arranged in a sequence like what we had when on the slide when they were connected in series. Who believes with who is convinced by this argument? You don't have much support, Adam. Any other justification for this connection to be in series? All right, let's try with in parallel. And William, you believe that they are connected in parallel, right? Yes. All right, so convince me that they are connected in parallel.
Because the right side of every...
All right, okay. William is on the right track. We have to compare potentials. So how about if instead of A and B, I would put plus and minus? So Adam is looking at potentials. And potential over here would be plus. Now potential here will be, can we see that? Right? Because this wire connects it with minus over there, right? So here we'll have minus. This one. Potential here will be minus, right? Because this wire connects it with minus. So these two potentials are equal. Now how about this potential? Plus, right? Because this wire connects it with that plate, right? So potential on the right-hand side of the second capacitor is equal to the potential on the left-hand side of the first capacitor. So I can recognize that these two are connected how? In parallel. These two are connected in parallel. Well, we don't know about the last one yet. Let's try with the last one. What is going to be potential here? Plus, yeah, because this wire connects it here. And what will be potential here? Minus, because it's straight over there, right? So we see that all three capacitors have the same potentials on corresponding plates. Now, I know that some of you usually play with think about, well, how can I transform the drawing so that it looks, well, the arrangement like we saw it on the slide. Because in principle, this arrangement is therefore equivalent to this one. Now, how to imagine, how to bend those wires to get it like that? Well, think about that. You grab this node and this node and pull it. Yes, so these two capacitors will arrange themselves like that. Can you see that? Do you imagine it? Yes, so these two plates will go over here, and these two plates, let's make it like that, will go over there. So indeed, we will get such an arrangement. Let me now give you another quick puzzle. Let's say that I have capacitors like that. Let's say that they are identical capacitors. And charge on this capacitor is going to be, let's say that is 1 microcoulomb. How the other two will be charged? Over here will be what? 1. Okay, William suggests that over here we'll have 1 microcoulomb as well. And what is the justification for it? It is actually something which I asked also on the test, and half of you didn't take advantage of that, of a property of the universe, of symmetry. Indeed, if we take a look, what will happen if I flip the system? I should not see the difference, right? Which means that because of that, these two have to be, I said microcoulomb. All right, William says that this capacitor now should have charge of 2 microcoulombs. Who believes William? Who doesn't believe him? Well, you either believe or not. Now, we say? Okay, William wants to change this, so William doesn't believe. What should I put here? 1. And the reason is? Potentials. Let's talk about potential. I don't want you to use word voltage for a while. Andrew has a suggestion.
Well, the total potential over the first one is then split equally between
potential difference.
Potential difference over the first capacitor is
between these 2 points.
Between those 2 points must be equal to, basically must be divided equally between the other 2.
Why?
Because charge is proportional, or the charge on the capacitor is proportional to the voltage. So.
Oh well, I mean, yeah. So if we knew that, then indeed William would be right. Yeah. Okay. So Andrew has a good justification. He came to the conclusion that potential difference across this capacitor must be equal to potential difference across this capacitor.
Well, it should be divided. It should be 2.
Oh, that it's 2 over here. So Andrew believes that it should be 2. Now, why potential difference across this capacitor is supposed to... Oh, now I'm lost. Because now definitely potential difference here is not equal to potential between these 2 points. Microcoulomb. Well, so let's recognize how they are connected. Yeah, so how these 2 are connected. They are in parallel. What's the justification? Potential on the left-hand side of the bottom one is equal to potential of the on the left-hand side of the top one. And potential on the right-hand side is equal to potential on the right-hand side. All right. So these 2 are connected in parallel. They behave like a single capacitor, right? I can imagine, therefore, that they are connected like that. And over here I have compared capacitance now of this system with the capacitance of this capacitor. Yes, Adam? So this capacitance is 2 times larger than this one. But it doesn't matter. Now, this system is connected in this system in series. Compare the charge on the system with the charge on this capacitor. They should be the same because the system and the capacitor are connected in series, which means that the charge on this capacitor is equal to the charge on the system. And on the system, if they are connected in parallel, they add up. So charge on the system is 2 microcoulombs. Therefore, charge on this capacitor is also 2 microcoulombs. And that's it.